Hello and welcome to this video about chemical changes. In this video we are going to look at how we write chemical equations, how we balance them and interpret them, and we will look at what moles and molar mass are. Let's just remember what chemical reactions are. Chemical reaction is just a change where we have one or more substances that are being converted into new substances. And instead of just saying substances all the time, we have special words for what we start with. They are called reactants. Those are the starting substances or substance. Products would be what is produced or made. It's the new substance or substances that are formed. Reactants form products. Remember the law of conservation of mass? The number of grams of reactants, the total grams of reactants, is going to need to equal the total number of grams of products because mass is conserved. This is actually an experiment that was carried out by the French chemist Antoine Lavoisier when he was showing this idea about the law of conservation of mass. So let's jump into how we write chemical equations. Let's take this experiment that Lavoisier did. And let's look at how we as chemists write this to make it easier for us to understand what's going on. We don't want to have to say all these words and put in a lot of vocabulary when we can write it in a much simpler way and see what's going on faster. First, we use chemical formulas instead of names. So we don't say mercury 2 oxide. We actually write the chemical formula for that. And we know that if mercury has a charge of +2 on it, we look at the periodic table, we see that oxygen forms a -2 ion, so they combine in a 1-to-1 ratio. We have 1 mercury for every 1 oxygen ion. That's going to form oxygen. Remember, oxygen is diatomic. There are 2 oxygens that go around together. So we write the symbol for oxygen, O, and a little subscript of 2, meaning there are 2 oxygen atoms that are combined and bonded together. Plus mercury, and we write the chemical symbol for elemental mercury. Now you'll notice there's a few other things here. We'll talk about those in a minute. Use this arrow. That means produces or yields. So their arrow is used in our chemical equation. We use a plus symbol to mean plus or and or with or added to. You can see we use that there. And we also describe the state of matter by adding a little symbol after the chemical formula. We use in parentheses an S to mean solid, a lowercase l in parentheses for a liquid, a lowercase g for a gas, and we use the lowercase aq in parentheses to mean aqueous. That means it is dissolved in water. So here we have the beginning of our chemical equation. Sometimes you will see these other symbols. If over the arrow sign you see heat, just means the reactants are heated, or light, it means the reactants are exposed to light. If you see ELEC, an electric current has been applied to the reactants. Now, here we have our equation, a chemical equation that we wrote. It is important to notice this equation is not balanced, absolutely not balanced yet. We're going to learn how to do that. How do we know it's not balanced? And what is balancing a chemical equation anyway? Well, this mercury 2 oxide right here is producing 2 products. But for every one of these mercury 2 oxide molecules, how in the world are we getting 2 oxygen atoms out of that? We can't. The number of oxygen atoms added together from this side of the equation must be equal to the number of oxygen atoms over on this side of the equation. So in order to get diatomic oxygen, I must have more than one of these molecules to start with. Now, this is an important rule. When balancing chemical equations at this point, you are allowed to make changes to your equation by only adding coefficients, not subscripts. You may not change the little subscripts in the molecules that you have sitting there, but you can add coefficients. And this is how we'll do that. We're going to add a coefficient. that's better. We're going to add a coefficient of 2 in front of our mercury 2 oxide. So now, is this going to be balanced? If I have 2 oxygens on the left side of this arrow, do I have 2 oxygens on the right side? I do. There are 2 oxygens right there. Now, what about the other atom? I have 2 mercury atoms on the left side of the equation, but there is only 1 mercury atom on that side. So I'm going to need to, remember, add a coefficient, not a subscript. I'm balancing my chemical equation. So for this reaction to take place, I'm going to have 2 mercury 2 oxides. It's going to produce a diatomic oxygen molecule and 2 elemental mercury atoms. And this is balanced. 2 mercuries, 2 mercuries, 2 oxygens, and 2 oxygens. That is my second step. Make sure there are equal numbers of each kind of atom on each side of the equation. When I'm finished, I check my work, which I did, and there I have my balanced chemical equation. So now that you know how to write a chemical equation and balance a chemical equation, let's look at interpreting a chemical equation. What does a chemical equation tell us, after all? Here's another chemical equation, and it has been balanced. We have 1 carbon and 1 carbon, 2 oxygens and 2 oxygens. This chemical equation tells us a lot of things. It tells us that for every 1 atom of carbon and 1 diatomic molecule of oxygen, I can produce 1 molecule of CO2, carbon dioxide. It also tells me something else. I know by looking at the periodic table that I'm starting with the atomic mass unit for carbon is 12.01, so I have that much mass in my carbon. I know that I have 2 oxygen atoms here. So when I look at the periodic table, I see that 1 oxygen atom has a mass of 16, rounded up to 16 atomic mass units. So here I have an atomic mass of 32 atomic mass units. I can also add up the atomic masses of carbon and the 2 oxygens, and I find that I get an atomic mass of 44.01 atomic mass units. But really, if I go in the lab, how easy is it going to be for me to deal with individual molecules and atoms, or with, heavens, atomic mass units? What are those? Can I measure those on my scale in the lab? No. So in the lab, we use grams instead of atomic mass units, and we use something called moles instead of molecules or atoms. And I'm going to tell you what that is. It's not this cute, fuzzy little creature. 1 mole, by definition, is equal to a specific number of particles or atoms or pieces. And this is that number, 6.022 times 10 to the 23rd. So every time I have 6.022 times 10 to the 23rd atoms, I have 1 mole of those atoms. Or if I have 6.022 times 10 to the 23rd molecules of carbon dioxide, that's 1 mole of carbon dioxide. This number means 6.022 with 20 zeros, more zeros after it. So, well, if I move the decimal point all the way to the end, I move this decimal point 23 places to the right, and I have that big of a number. So it's a really large number. So we write it in scientific notation to make it easier. So now I'm going to take all this information we were just looking at about 1 atom of this plus 1 molecule of this makes 1 molecule of this, right? And I'm going to add a new idea to this chemical equation. I can also say 1 mole of carbon plus 1 mole of oxygen is going to give me 1 mole of carbon dioxide. I could also say 6, because I know that 1 mole equals 6.022 times 10 to the 23rd pieces. I can also say that 6.022 times 10 to the 23rd atoms of carbon and 6.022 times 10 to the 23rd molecules of oxygen is going to give me 6.022 times 10 to the 23rd molecules of carbon dioxide. So this brings us to the important concept of molar mass. What is molar mass? Molar mass, by definition, is the mass in grams of 1 mole of a substance. So, what is the molar mass of carbon? pause this and think about it for a minute. Well, look down here. You know that 1 mole of carbon has 12.01 atomic mass units. It is also going to be equal to 12.01 grams. 1 mole, by definition, of carbon is equal to 12.01 grams. That is the molar mass of carbon. What's the molar mass of diatomic oxygen? Well, you know when you look at the periodic table that 1 oxygen atom is 16 atomic mass units. 1 mole of diatomic oxygen, because there are 2 oxygens there, is going to give me 32.00 grams. That is the molar mass of diatomic oxygen. What's the molar mass of helium? Well, I have to look at the periodic table for this, but 1 mole of helium equals 4.003 grams. When you look at the periodic table, the atomic mass units in helium is 4.003 atomic mass units. So 1 mole of helium contains 4.003 grams. And why is this important? Because now that you know what molar mass is, you have a very powerful tool to convert between grams of a substance and the number of moles of a substance. So, if I tell you I have so many grams of methane, like 50 grams of methane, you can convert that into the number of moles using dimensional analysis. I'm going to multiply 50 grams of methane by a conversion factor. And this conversion factor, remember, is equal to the number 1. The number in the numerator is going to be equal to the number in the denominator. And I know something about methane. I know the molar mass. I know that if I look at the periodic table, carbon has a molar mass of 12, and every hydrogen has a molar mass of 1.0. I'm just going to round to the nearest whole number here. And that means that I have 12 plus 1 plus 1 plus 1 plus 1 for my 4 hydrogens. It gives me 16 grams. So if that is my conversion factor, I can put my 16 grams on the bottom, and I can put my 1 mole of methane on the top. And look what I get. I get grams canceling out on the top and the bottom. Remember, this is like saying it's over 1. I'm going to simply multiply my numerators together. I will multiply my denominators together. That gives me 50.0 over 16.0, and the only unit I have available is moles. 50 divided by 16 is 3.13 moles of methane. That's how I convert from grams to moles. Now, what about if I'm given the number of moles and I want to convert to grams? I'm going to do the same thing. I'm going to find my molar mass. So I have my conversion factor, and my molar mass for calcium, in this case I'm looking at calcium. 1 mole of calcium, when I look on the periodic table, is equal to 40.1 grams of calcium. So I can use this to set up my problem. I know that I have 3 moles of calcium. That's like saying 3 over 1. It's going to be a great, big, giant, exciting fraction. And I am going to put my moles of calcium on the bottom because I want to cancel the units of moles out. These units will then cancel. And I'm going to put 40.1 grams of calcium on the top. You can see that I'm going to get 3 times 40.1. That's 120.3. When I multiply these numbers across, 1 times 1 is just 1. My moles canceled out. The only units I have are grams of calcium. So my answer is 120.3 grams of calcium. Advanced ideas. What's the chemical formula for sucrose? What's its molar mass? Write a balanced chemical equation for photosynthesis. There's something you can do. Or what about safety airbags in automobiles and this chemical equation? Sodium azide is what is used, and this is a little bit more difficult to balance, but see if you can balance that. Or maybe you have some other ideas. Look forward to seeing what you come up with, and we'll see you in class.